All right, hello everyone. Welcome to week 5 for maps mapping and geospatial technology. Today we are going to be covering geographic information systems or GIS. So, think back to last week's class and ask yourself this: what do we use geospatial data for? So retail companies identifying new locations for businesses, identifying the closest restaurant or hotel based off of our current location, and there are so many more examples that could be given. All of these concepts involve the nature of geospatial data and the ability to analyze or compare particular locations and their attributes. Geospatial technology is used to address these ideas and solve these types of problems and many, many more. Whenever examination, manipulation, or analysis of geospatial data is involved, for instance, if you need to tie non-spatial data to a location, or if you want to use this information to create a map of your analysis, geographic information systems, or GIS, are essential to getting these tasks done. The formal definition for GIS is a computer-based set of hardware and software used to capture, analyze, manipulate, and visualize geospatial information. So, how can GIS be defined? An integrated collection of computer software and data used to view and manage information about geographic places, analyze spatial relationships, and model spatial processes. A GIS provides a framework for gathering and organizing spatial data and related information so that it can be displayed and analyzed. GIS can also be defined as a computer application capable of performing virtually any conceivable operation on geographic information, from acquisition and compilation through visualization, query, and analysis to modeling, sharing, and archiving. Or lastly, they can be geographic information systems were originally conceived as digital toolboxes for handling maps, and the principles underlying such systems and framing their design and use became known as geographic information science, GI science. So, what can GIS do? Can integrate data from various sources. You can edit and update data, draw maps and visualize spatial distributions, accurately measure distances in areas, overlay maps and compare data, and perform sophisticated analysis and modeling. GIS is a powerful tool for analyzing geospatial data. This ability to utilize geospatial data explicitly is what separates GIS from other information systems or methods of analysis. For instance, a spreadsheet enables you to tabulate housing values and the amount of money paid for a house at a particular address. But even though you're using data, that has something to do with a location. There's nothing in the spreadsheet that allows you to examine that data in a spatial context. GIS is by its nature 100% computer-based, whether it involves software running on a desktop, laptop, mobile device, or served off the web. The system being referred to is a computer system. The information handled by GIS is geospatial information, something that has direct ties to using GIS online. There are numerous online GIS resources for viewing and analyzing geospatial data. An example of a local GIS is from Mahoning County, Ohio. You can open your web browser and go to gisap.mahoningcountyoh.gov/mahgis. So the term GIS first appeared in the early 1960s with the implementation of CGIS, or Canadian Geographic Information System, which was designed to provide large-scale mapping of land use in Canada. The development of CGIS is attributed to the late Roger Tomlinson, who became known as the father of GIS. So this is Roger Tomlinson, the father of GIS. He coined the term Geographic Information System. And in 1960, Roger Tomlinson was working at the Aerial Survey Company, and the company was focused on producing large-scale photogrammetric and geophysical maps. In the early 1960s, Tomlinson and the company were asked to produce a map for site location analysis in an East African nation. Tomlinson immediately recognized that the new automated computer technologies might be applicable and even necessary to complete such a detailed-oriented task for more effectively and efficiently than humans. Eventually, Spartan met with IBM offices in Ottawa and began developing a relationship to bridge the previous gap between geographic data and computer services. Tomlinson brought his geographic knowledge to the table as IBM brought the computer programming and data management. There are a couple of components to GIS, first of which being the hardware. The hardware is the computer on which the GIS operates, centralizing computer server, standalones, networks, and more. And then the software provides the functions and tools needed to store, analyze, and display GIS. And then people are involved in order to gather the data and create the methods and procedures used to analyze GIS. But this can be broken down into a lot more different categories. Hardware is the computer, and then software provides the functions to analyze the GIS. Possibly the most important component of a GIS is the data. Geographic data and related tabular data can be collected in-house or purchased from a commercial data provider. A GIS will integrate spatial data with other data resources and can even use DBMS, used by most organizations to organize and maintain their data to manage spatial data. GIS technology is of limited value without people who manage the system and develop plans for applying it to real-world problems. GIS users range from technical specialists who design and maintain the system to those who use it to help them perform their everyday work. A successful GIS operates according to a well-designed plan and business rules, which are the models and operating practices unique to each organization. In the early days, there was no user interface as we know it now. GIS consisted simply of collections of computer routines that a skilled programmer could use to build an operational GIS. Each GIS was unique in terms of its capabilities and levels of resources. GIS migrated to the command line in the late 70s, early 80s, which served as the user interface. Essentially, GIS was a toolbox of geoprocessing operators or commands that could be applied to datasets to create new datasets. GUIs, or graphical user interfaces, finally came in the late 80s to supplement command line. Menus. We finally got menus, plus the ability to customize using Java and Visual Basic to published applications, application programming interfaces or APIs that exposed key functions. Now we use the web and Python. GIS software of today still embodies the same principles of an easy-to-use menu driven by user interface and customization capability, but can now be distributed over the web. GIS software packages provide a unified approach to working with geographic information. And then we have this hands-on activity. I will go ahead and pull it up. So in this activity, you guys are going to, this lab has you use a free online Navimatrix GNSS mission planning tools to examine how to use GNSS satellite positions and other planning factors for data collection. In addition, you'll use some sample web resources to examine related GNSS concepts for your local area. So if you guys have some time, definitely check this one out. It's worth a look. So GIS provides a means of representing real-world data in a computer environment so that it can be easily analyzed or manipulated. A model is a kind of representation that simplifies or generalizes real-world information. For instance, if you were tasked with making a map of all the stop signs in your city, you'd need to be able to represent the locations of all the signs on a map at the scale of the entire city. By laying out a map of the city and placing a dot at each sign location, you would create a good representation of them. The same holds true if you had to come up with a map of all the roads in your town. You could attempt to draw the roads at their correct width, but the roads' locations can be represented simply and accurately by lines drawn on a map. In the discrete object view, the world is made up of a series of objects, each having a fixed location or fixed starting and stopping points, or some sort of fixed boundary. A street starts at one point and ends at another, and there is a definite boundary between your property and your neighbors. Around a university campus, numerous objects represent buildings, parking lots, stop signs, benches, roads, trees, and sidewalks. By viewing the world in this way, real-world items can be modeled in the GIS as a series of objects, such as a collection of lines to represent a road system or a series of points to represent fire hydrant locations. When adapting the discrete object view of the world to a data model, items in the real world are represented in the GIS by one of three objects. Points, these are zero-dimensional objects, simple sets of coordinate locations. Lines, these are one-dimensional objects created by connecting starting and ending points. And polygons, these are two-dimensional objects that form an area from a set of lines or having an area defined by a line forming a boundary. These three items are referred to as vector objects, and they make up the basis of the GIS vector data model. Basically, the vector data model is a means of representing and handling real-world spatial information as a series of vector objects. Items are realized in the GIS as points, lines, or polygons. Points are defined by a single XY coordinate pair. Lines are defined by two or more XY coordinate pairs. And polygons are defined by lines that close to form the polygon boundaries. In the vector data model, every feature is assigned a unique numerical identifier, which is stored as the feature record in an attribute table. Digitizing is a common way to create points, lines, and polygons of vector data. With digitizing, you are in essence tracing or sketching over the top of areas on a map or another image to model features in that map or image of the GIS. For instance, if you have an aerial photograph of your house being shown on the screen of your GIS software, you can create a polygon by using the mouse to sketch the outline of your house and save it in the GIS as a representation of your house. When objects are created in GIS, they can be set up with coordinates, but GIS still needs to have knowledge of how these objects connect to each other and what the relation each object has to the others. For instance, when two lines are represent crossing streets are digitizing. For instance, when two lines that represent crossing streets are digitized, the GIS needs to have some sort of information that an intersection should be placed where the two lines cross. Similarly, if you have digitized two residential parcels, the GIS would require some information about the two parcels being adjacent to one another. This notion of the GIS being able to understand how objects connect to one another independently of their coordinates is referred to as topology. With topology, geometric characteristics aren't changed no matter how the dataset may be altered. Topology establishes adjacency, how one polygon relates to another polygon in that they share a common boundary, connectivity, or how lines can intersect with one another, and containment, how locations are situated inside a polygon boundary. There's also a second way of viewing the world, in which not everything has a fixed boundary or is an object. For instance, things such as temperature, atmospheric pressure, and elevation vary across Earth and are not best represented in GIS as a set of objects. Instead, they can be thought of as a surface that's made up of a nearly infinite set of points. This way of viewing the world is called the continuous field view. This view implies that real-world phenomena continuously vary. Rather than a set of objects, a surface filled with values is used to represent things. For instance, elevation gradually varies across a landscape from high levels to low from high. There's also a second way of viewing the world, in which not everything has a fixed boundary or is an object. For instance, things such as temperature, atmospheric pressure, and elevation vary across Earth and are not best represented in GIS as a set of objects. Instead, they can be thought of as a surface that's made up of a nearly infinite set of points. This way of viewing the world is called the continuous field view. This view implies that real-world phenomena continuously vary. Rather than a set of objects, a surface filled with values is used to represent things. For instance, elevation gradually varies across a landscape from high elevations to low elevations, with hills, valleys, and flatlands, and at every location we can measure the height of the land. When continuous fields are represented in GIS using the three vector objects, and thus a vector data model, is often not the best way of representing data. Instead, a different conceptualization called the raster data model is usually used. In the raster data model, data is represented using a set of evenly distributed square grid cells, with each square cell representing the same area on the Earth's surface. For instance, to represent an entire section of the landscape, each grid cell might represent 10 square feet or 30 square meters. Or 1 square kilometer, depending on how the grid cell size being used for the model. Regardless of the grid cell size, each cell has the same resolution. That is, the same grid data set cannot mix cells of 30 square feet together with cells of 5 square feet. Also, each grid cell contains a single value representing the data being modeled. For instance, in an elevation raster, each grid cell could contain a value for the elevation at that area on the ground. Data sets such as land cover, soils, or elevation are all commonly represented using the raster data model. The National Land Cover Database, or NLCD, is an example of a raster data set used in GIS. Developed by a consortium of U.S. agencies, NLCD provides 30-meter raster data covering the entire United States. And each grid cell is coded with a value that corresponds to a specific land cover type at that location. NLCD designations include categories such as open water, developed high intensity, deciduous forest, pasture or hay, and woody wetlands. NLCD provides a means of broad land cover classification at state, regional, or national scales. The GIS has information about the spatial properties of the object in each layer, but it does not have any other information about those objects, such as the tax assessed value of a house, the house's address, the name of the owner, the number of people living in the house, the material the driveway is made of, or how old the driveway is. All of these attributes represent other non-spatial information associated with each of the objects. When representing attribute data in GIS, these values can take one of 4 forms: nominal, ordinal, interval, or ratio data. Nominal data is a type of data that is a unique identifier of some kind. If numerical, the differences between the numbers are not significant, such as a social security number or a telephone number. Ordinal data is a type of data that refers solely to a ranking of some kind. Hierarchy, ranking, etc. only tells rank, not the measurement of data. Interval data is a type of numerical data in which the difference between numbers is significant, but there is no fixed, non-arbitrary 0 point associated with the data, something like temperature. Or ratio is a type of numerical data in which the difference between numbers is significant, but there is a fixed, non-arbitrary 0 point associated with the data, such as age or weight or time. Another hands-on activity. So for this one, we've already discussed how to download GIS data from the national map. This was back in a couple different presentations ago. I think it might have been like week 2. You can also use the features of the national map to view different GIS layers. You can view the different GIS layers online rather than download the data. To get started, go ahead and go to this link. You guys can also check out the speaker notes I have in the PowerPoint as well for more in-depth instructions. And then, yeah, just go ahead and check it out if you guys have some time. So moving on. Each layer in a GIS has an associated attribute table that stores additional information about the features making up that layer. The attribute table is like a spreadsheet where objects are stored as records or rows, and the information associated with the records, such as the attributes, is stored as fields or columns. New fields could be created having headings such as owner and appraised value, so that this type of descriptive non-spatial data could be added for each of the records. Each new attribute can be one of the 4 data types, for instance owner, would be a nominal data, and appraised value would be ratio data. In this way, non-spatial data is associated with a spatial location. An attribute table for raster data can't be handled the same way as an attribute table for vector objects because a raster data set is composed of multiple grid cells. For instance, a 30-meter resolution grid of a single county could take millions of cells to model. Rather than having a separate record for each grid cell, raster data is often set up in a table with each record featuring the value for a raster cell and an attribute, showing the count of many cells comprise the data set. For instance, a county land use data set might contain millions of cells, but might consist of only 7 values. Thus, the raster would have 7 records and another field whose value would be a summation of how many cells have that value. New attributes would be defined by the raster values. For instance, the type of land we use each value represents. You can also join tables to connect the non-spatial data using common fields, something like tax records, for example. So for integrating data, it combines the layers of information that didn't look right. There we go. So for data integration, it combines layers of information to have a better understanding of location, something like satellite imagery, photographic images, maps, or tables, or spreadsheets. There are 2 primary GIS desktop applications. There is ArcGIS Pro, which is made by Esri, as you guys already know. Hopefully you're already a little familiar with it, since we've had one assignment and a couple of quiz questions that utilize it. And then the second one is QGIS, which is open source. So Esri, located in Redlands, California, where I currently am at. It was founded by Jack and Laura Dangermond in 1969. By 1982, Esri had released the first of its ARC products, the initial version of ArcInfo, a key GIS software package. Esri's GIS software has gone through many changes and evolutions over the years to reach its current form. ArcGIS is an entire GIS software package. In a platform, multiple pieces are brought together: software on a desktop computer, cloud-based software, mobile apps, and more that all use the same common techniques and are tied together. Think of ArcGIS as a GIS platform that you can use in a variety of different ways, whether on a desktop computer, in a web browser, as an app on a tablet, or as a developer toolkit. The main part of the ArcGIS desktop is a new standalone GIS program called ArcGIS Pro, which is the latest GIS from Esri. ArcGIS Pro has a 64-bit architecture and features a modern software interface that uses ribbons, tabs, and groups similar to programs like Microsoft Word and PowerPoint. ArcGIS Pro is ArcGIS Pro is compatible with web-based GIS maps and data, and enables you to publish web maps directly from ArcGIS Pro and also to download GIS data from the web directly into the program. It also features native 3D visualization of GIS data and offers multiple tools for analysis, editing, and management of data in both 2D and 3D formats. No questions asked, QGIS has the edge for consuming data. QGIS is versatile. It's cutting edge when it comes to consuming data, including spreadsheets. Both are able to do the standard GIS tasks, or managing data, joining data, projecting data, raster processing, and creating a map. Both are able to have customizable code, both modern, using 64-bit processing, and having 3D integration. The Python programming language is used for writing computer code for working with ArcGIS. Python is commonly used with ArcGIS and is simple to use for programming tasks. You could write short scripts within ArcGIS desktop itself, or use free tools found online to write scripts separately and then run them in ArcGIS desktop. Some common vector data formats. There is the shapefile, and it is a mandatory Esri file that gives features their geometry. Every shapefile has its own .shp file that represents spatial vector data. .shx, these are mandatory Esri and AutoCAD shape index position. This type of file is used to search forwards and backwards. The DBF is the standard database file used to store attribute data and object IDs. DBF file is mandatory for shapefiles, and you can open a DBF file in Microsoft Access or Excel. The PRJ file is an optional file that contains the metadata associated with the shapefile's coordinates and projection system. This file does not exist. You will get the error unknown coordinate system. If you want to fix this error, you have to use the define projection tool, which generates a PRJ file. GeoJSON is a lightweight format based on the JSON scripting language used by many open source GIS packages. GeoJSON's feature includes points, lines, strings, polygons, and multi-part collection of these types. Therefore, it represents addresses, locations, streets, highways, countries, tracts of land, and many more like this. GeoJSON features doesn't only represent physical world, but mobile routing and navigation apps also describe their service coverage using GeoJSON. And then KML, this GIS format is XML based and is primarily used for Google Earth. KML was developed by Keyhole Inc., which was later acquired by Google. KML is an XML notation for expressing geographic annotation and visualization within two-dimensional maps and three-dimensional browsers. KML has its own zipped version, KMZ, which replaced KML and now is the default Google Earth geospatial format because it is much more compressed version. KML is an international standard of OGC. KML specifies an interesting set of feature like place marks, image, polygons, textural description, and many for displaying in many geospatial softwares. KML comes with an extension KMZ. So the file GeoBase data, this consists of a single folder filled with files that contain all the geospatial information for a data set. For example, a geodatabase called Orange County could store the county boundaries as a polygon feature class, highways in the county as a line feature class, and the city streets as another line feature class. A file geodatabase provides essentially unlimited storage. Each feature class can hold a maximum of 2 terabytes of data, but there is no limit on how many feature classes a file geodatabase can contain. Geodatabases can also contain feature datasets or subgroups of feature classes organized together. For instance, in the Orange County geodatabase, if you have multiple feature classes, each highlighting different road types and planning features, you could have a feature dataset called transportation to group all the transportation related feature classes together in under one heading. In addition, geodatabases can store other data used in GIS, such as tables and rasters, and they can have GIS data in other formats, such as shapefiles or CAD data, imported into them. A geodatabase therefore serves to organize your GIS data and hold all the various layers you're using in a project in one place. Applications of GIS. So there are research tools in planning, something like constructing models of urban growth, anticipating impacts from natural disasters, making predictions for crop yields. There is spatial decision support systems. This goes into infrastructure for roads, towns, and services, census, population statistics, and medical resources. There's the emergency response systems, 911. There is gaming, augmented reality, something like Pokemon Go. You have routing for something like truckers or delivery services, and then disaster evacuation planning, and then politics, so county boundaries and gerrymandering. Examples of GIS applications. A community planner might want to assess the anthropogenic impact on lands that should otherwise be protected. She may also want to understand why these impacts are only in certain areas and not others. A biologist might be interested in the impact of the wildfires on the populations of deer species to obtain a better understanding of long-term threats to those populations. An epidemiologist might want to understand the spread of diseases, especially if it reaches the level of global pandemic. Telecommunications company might be interested to learn the best locations for 5G towers when building out their network. And a fast food company franchisee may want to understand traffic patterns when determining where to build their next location. And for the last slide, I will leave you guys with a quote. With a single collection of tools, GIS is able to bridge the gap between curiosity-driven science and practical problem solving. So that is going to wrap up the lecture. There is going to be 2 assignments associated with this week, since we had the quiz last week, playing a little bit of catch up. So I do apologize, they are backwards. So assignment 5 is actually going to be based off of last week's lecture for week 4. It should be relatively easy, so it's it's got a shorter due date. It's going to be due on, I believe I made it for this Sunday the 16th, so you'll have about 7 days to do it. It's already up as of me recording this. So basically you're just going to pick a non-traditional map, which I went over in last week's lecture. and then you'll give about a 250 word discussion analyzing the map's design, purpose, and unique insights it offers. If you guys have any questions, do reach out to me about it. I'm happy to answer them. And then for the next assignment, again, I apologize, they're backwards in order. This one is based off of this week's lecture. It does have a data set associated with it, so make sure you download that. And this one is going to be similar to, I want to say it was assignment 3, where you will need access to ArcGIS Pro. You guys should all have access and have your accounts set up by now. Please, if you don't have access to it, please reach out to me sooner rather than later, so that I can make sure you guys get access to it. It is a little bit more difficult for me to do it on my phone if I'm out and about on the weekend. So definitely try to reach out to me sooner than later if you are having trouble accessing it. And this one is going to be due on the 23rd, so you'll have about 2 weeks to do it. With all of that said, that is pretty much all I have for week 5. So if you have any questions, feel free to reach out to me. I will be available for office hours on Friday of this week on the 14th, and then by appointment as well. So yes, enjoy your week, everyone.